An average aircraft would disintegrate doing maneuvers like a barrel roll or cartwheel. But the Sukhoi stunt plane can do that and more. This machine outturns, outpushes, and outworks ocean liners 1,000 times its size. If you've got a big ship that needs parking, then you need a tugboat. Some love the Carousel. Others fear it. Maybe for a good reason. Hanging on a single pole, this ride is a 10-ton balancing act. Let's open up these machines and see how they work. Born in the Soviet Union in the 1980s, the Sukhoi SU-26M is still the most sought-after stunt plane in the world. The 26 hits 450 kilometers an hour, does a 360 barrel roll in under 1 second, can hang in place, and takes more G-force than an F-16 fighter. It's built to sail through conditions that no regular plane could survive. Let's see how it works. To get a plane off the ground, you need two things: propulsion and wings. Engines, either jet or propeller, provide the motion, which increases airflow over the wings. And the wings provide the lift. The shape of the wings combined with fast-moving air produces downwash and reduced air pressure on the wing's top surface. These aerodynamic forces produce lift. The amount of air diverted depends on the angle of the wing. This is known as the angle of attack. At takeoff, pilots adjust the wings to increase their angle of attack and get the machine airborne. Now that it's up, designers had to figure out how to keep it there while allowing it to perform incredible stunts. There are 3 basic challenges. First, extreme angles like these will either crash a regular plane or tear off its wings. The shape and construction of the wings is critical to overcoming the violent forces of these transitions. Second, the controls on this plane are surprisingly basic. No electronics, no power assist. Hydraulic systems can fail under extreme loads. So how does a pilot manage without them? And third, all this engineering is meaningless if you can't keep the pilot alive. First challenge, keep the machine in one piece. The key to that begins with the stunt plane's wings. This is the profile of a regular aircraft wing. It's got a curved top and a flat bottom. This shape works great for lift, but good luck trying to fly upside down. If you tried to fly at this angle, you'd be heading in the wrong direction. Stunt plane wings are heavily curved and more or less symmetrical, so lift remains the same upside down or right side up. Another force working against flight is aerodynamic drag. The only way to perform tricks like this is to increase it. Create too much, you stall, and then you drop like a stone. So, stunt planes need low-drag wings, heavy-duty construction, and powerful engines to keep them from shutting down when they're upside down, sideways, and all twisted up. But what keeps it from falling apart? On this machine, the wings are covered in titanium reinforced with Kevlar, almost impossible to bend. These ultra-stiff wings transmit extreme forces onto the plane's spar, the main supporting structure of a wing. It's anchored to the fuselage at the plane's center and evenly spreads out stresses working against the wings. It kind of works like a seesaw. The forces on each side of the spar cancel each other out. All modern planes have spars, and they're all strong. But the 2.6s are made from solid graphite and can withstand forces of over 35 Gs. On to the second challenge, controlling the machine. From down here, airshow stunts may look like they're computer-controlled, but inside the 2.6, there's nothing but a stick and a couple of pedals to control the plane's movement. The stick is connected to elevators. Pull back, and they go up. That forces the tail wing to drop and the plane's nose to rise. This changes the wing's angle of attack, creating more drag and lift. Foot pedals control a rudder that moves from side to side for turning. The stick also connects to ailerons located on the wings. Ailerons help normal aircraft bank. They always move opposite to each other. One goes down, the other goes up. This increases lift on one wing and drops the other, allowing the plane to turn. In the 2.6, a sideways push on the stick engages the ailerons. Not that different from other planes, but they can't take it to these extremes. This machine's wings allow it to take a bank into a barrel roll, and a lift becomes a loop. And there's more. A sharp turn of the rudder with the push on the elevators turns a barrel roll into a crazy tumble. The machine really can do just about anything the pilot dreams up. And what the pilot can physically overcome. There's no power assist in the controls of the 2.6. Its builders didn't trust hydraulics or electronics on extreme moves, so they didn't install any. But they did give pilots a little bit of help with some clever add-ons. At the plane's tail, the front edge of the elevators flare out into these edges called horns, a kind of aerial power steering system. Watch how they help the 2.6 pull out of this dive. When the pilot pulls hard on the stick, it raises the elevators, but that's not enough power. At certain speeds and angles, where strength alone would fail, the horns help push the elevators the extra little bit, giving the pilot just enough control to keep the machine airborne. With its wing design, super strong construction, and a couple of engineering tricks, the 2.6 throws the aeronautical rule book out the window. But there are other physical laws you can't throw out, no matter how special the machine. And that brings up the third challenge, gravity. Moves like these come at a price. The faster you change speed or direction, the more G-force you create. The resistance you feel as your body catches up to the plane is G-force. So, the next design challenge for the 2.6, protect the pilot during intense moves. On steep climbs, blood drains down the body and oxygen to the brain gets cut off. First, you go blind. Then you pass out. When diving, too much blood rushes to the brain. Eyes fill up, and you literally see red. The amount of G-force is directly related to the pilot's alignment with the machine's acceleration. So, the designers angled the 2.6's seat at 35 degrees. By reducing the direct line to G-force, the amount of blood that gets pushed around is reduced. Another line of defense for this nearly indestructible machine. But this Soviet icon also had to overcome some ice-cold problems. Find a proven, high-powered, lightweight engine that won't freeze up in winter, and then figure out how to start that engine on a frigid Siberian morning without a battery. To start with, build up a 360 horsepower radial engine with World War II pedigree that has 9 pistons arranged in a circular pattern. Just like the pistons in your car, these work in 4 strokes. They pull in air and gas with the first stroke, compress it with the second, ignite it with the third, push it out with the fourth. But firing in a circle sequence is trickier than a conventional inline engine. Watch them fire. First, every second piston goes off. The next time, those same pistons are skipped over while they expel the exhaust and suck fuel for their subsequent firing. Fighter pilots love this engine. Even if a piston or two got shot out, you still had enough to get home. Everything on this plane is manually controlled. No hydraulics to leak, no electronics to break down. The air-cooled engine even has a manual thermostat. The pilot opens and closes metal shutters like the aperture of a camera to adjust the engine's temperature. The Soviets had found their perfect engine, tough, dependable, and powerful for its size. Next, the battery, critical for turning over most combustion engines. But they needed to start these things in winter, and new batteries would drain in the cold. So designers came up with a surefire solution: air pressure. This ball contains compressed air that's injected into the cylinders to move the pistons, and that starts the engine. Once it's turned over, fuel smoothly replaces the air. There is a small battery attached to the engine, which showers the combustion chambers with sparks to ignite the air-fuel mixture. Smart, no-frill mechanical ingenuity. And here's another one: visual guides attached to the wings. These help pilots orient the machine flying upside down or coming out of a spin by lining up the guide with the horizon. And the horizon is the only thing that's ever limited this machine. Whether hanging from its propeller helicopter style or taking an earthbound dive, it's all about the performance. As for the airshow smoke, a high-speed pump injects paraffin oil into the hottest part of the exhaust pipe. The oil has a high flash point, so it doesn't go up in flames, but the pipe is hot enough to make it smoke. That may be the flashiest feature in a bare-bones, no-nonsense, unbreakable aerial hot rod that has dominated skies both east and west for over 2 decades. These are the sheepdogs of the marine world. Without harbor tugboats, megaships could never get into port. And we'd run out of oil, food, and pretty much everything else in a matter of days. As the size of ships have increased, so have the demands put on tugs. Conventional harbor tugs working here in Vancouver need all the help they can get. And it comes from this tractor tug, the newest and toughest member of the family. A sumo wrestler and dancer all in one that can push and turn a Leviathan 1,000 times its size. Let's see how it works. Tugboats need 2 things to get their job started: a big, powerful engine and a special hull design that allows them to dig into the water. Essential to help monsters like these parallel park. These harbor tugs pack around 1,800 horsepower. This tractor tug is driven by 2 3,000 horsepower diesel engines. Precision-tuned with computer-monitored fuel injection and turbochargers, each one of these engines could power a full-size locomotive. But a locomotive has a huge advantage over a tug. It's got wheels that are always in contact with solid steel rails. Friction between the wheels and the rails make it easy to generate traction. Tugboats have to do it on water, which is always moving and, well, kind of slippery. All the horsepower in the world means nothing if you can't somehow get a grip and create leverage. The secret to winning that battle is in the hull. Tugs are kind of like icebergs. A big part of them live underwater. They ride low under the enormous weight of their engines, and as they power up, they sink even further. That's because they're built with something called a heavy displacement hull. Instead of riding on top of the water, it sinks into the trough of its own wake. More contact with the water means more friction and more pushing power. But to guide ships in and out of narrow harbor entrances, modern tugs need a lot more than power and grip, including independently controlled props, keels that go on the front of the boat, and indestructible winches. There's another kind of friction the tug needs. The kind that keeps you glued to the wall of a ship. And whether you're an old tug or brand new, there's no substitute for rubber tires. Even with all that friction and horsepower, these machines often work in teams. They have to on this big fella that's all loaded up and ready to head back to sea. The tugs take aim at clearly marked sweet spots and quickly push the freighter into a shipping lane. That's the work of a basic harbor tug. Heavy displacement hull, big engine, lots of tires. But with moves like these, this tractor tug is destined for something more. When it's not managing this massive parking lot, it goes out to meet ships and guide them through narrow harbor entrances. If it needs to slow them down, it just hangs on with the winch, pulls the other way, and becomes an aquatic emergency brake. To be effective, escort tugs require advanced engineering, starting with these azimuth Z-drive thrusters. Thrust comes from huge propellers. These cones increase their power. And the whole rig can spin a full 360 for total control on the water. They allow an experienced hand to steer on a dime, move forward, backward, and sideways. 2 controllers, each connected to a Z-drive. Twist the control to turn the blades. Push them forward to control thrust. Commands are sent electronically to 2 sets of gears, an outer ring gear that controls direction, and an inner drive shaft that connects the engine to the propeller blades. The azimuths are great for pushing around boats, but they're even better when teamed up with the tug's powerful winch. Driven by a large 250 horsepower motor and equipped with a 300-meter fabric line, it's light enough to float, and unlike steel cables, it doesn't rust. This rope is so strong, you'd need the thrust of 10 F-16 fighter jets to pull it apart. And that comes in handy for this tug's most advanced move. It starts by hooking up to the back of a ship, then moves out to one side. And finally, with the help of its powerful drives and front keels, digs in and rotates the ship like a giant rudder, turning vessels 10 times faster than it ever could with a simple push. Tugboats may look small when sitting next to mega ships, but they're all muscle and fancy footwork, helping take goods out and bringing them in. A big gear in our economic engine. This may be the most popular machine ever designed for kids and the young at heart. Carousels have been enchanting riders for hundreds of years. Let's see how they work. Crawl inside one of these things, and you learn that there's no magic making it go round. It's a mechanical monster with pretty cool secrets. To start with, let's look at how the machine goes round and round. A lawnmower-sized engine turns a shaft that drives a small gear that grooves around the inside of a large planetary gear. That's all it takes to spin 10 tons of machinery. The seamless sets of teeth meshing together upgrade the small motor's output into all the force required to run the show. The gears are incredibly durable, and their smooth interlacing ensures that turning doesn't make the machine wobble. There aren't any wheels under this ride's 36 horses, so it's critical that everything stays in balance. To stabilize the carousel, a center pole connects to these beams called sweeps. Cables hold up the sweeps from above, like a miniature suspension bridge. Everything else is connected and hangs on for the ride. The center pole is locked in place by 2 variable beams called mudsills. These allow the ride to be quickly and easily leveled by adjusting one side or the other. And keeping things level is key to the machine's smooth reputation. The animals also play a part in this delicate balancing act. Each horse has a partner whose movement has to be mirrored on the opposite side of the ride. When one goes up, the other has to go down, or the ride will start to vibrate. So on this machine, that means 18 pairs of synchronized horses that are connected to hooks on a crankshaft. The crankshafts are connected to bevel gears that transform round and round into up and down. The horses themselves may look heavy, but on a traditional carousel, they're hollow and carved from material like basswood, as strong as it is light. Once everything is up and running, there's very little friction for the machine to overcome. So the ride could technically spin fast enough to throw riders from their saddles. Good thing this magnetic counter cuts off the power if the carousel cracks a breathtaking 11 kilometers an hour. A lot of people are curious about the lights. How the heck do you rig a spinning platform without tangling the wires around the pole? Think about your lit-up Christmas tree. Try spinning that for a couple of hours. What a mess. For a carousel to keep them on and the ride moving, it needs a specialized component that allows the machine to have electricity without wires wrapping around the pole. It's called a commutator, and it works by transferring electrical current wirelessly to metal brushes that spin along with the rest of the ride. Power enters the carousel through the main pole. It then travels through the commutator to the brushes. Current then flows to an electrical panel that sends it along wires to power the lights. Which on this particular machine has been happening since its creation in 1908. That's a long time to be spinning, but the carousel itself dates back to the Middle Ages. The ride's hundreds of parts make enough racket to sound like a medieval battle, which is spot on, because this gentle ride was first built as a machine to train knights for war. Centuries ago, young riders in training rode a merry-go-round for target practice. From a wooden horse, they tried to spear brass rings. It's where reach for the brass ring comes from. Thanks to an ageless design that keeps it going round and round, these young riders can dream all they want about faraway castles and have a great time while doing it. This plant has dozens of machines that turn rock and stone into cement, concrete's essential ingredient. This machine moves people and cars across some big water. The Super C-Class double-ended ferry does it best. A raging jet fuel fire burns up a plane in seconds. To put it out, you need a special firefighter with some reach, the Oshkosh Striker. Let's look inside these machines to see how they work. This is the St. Mary's cement plant on the Canadian shores of Lake Ontario. Cement is the essential ingredient in concrete. Concrete is basically sand and gravel. Cement is the glue that holds it all together. And plants like this one have to be able to make a lot of it, because we need a lot of it. The world uses about 3 billion tons of it every year. The recipe? Crush piano-sized rocks, blast dust through man-made tornadoes, and cook it into a molten lava. All to make a material that's built the world we know. It's the most versatile building material in the world. So this plant's machines run weeks on end, day and night, without ever stopping. Let's take a closer look. To make cement, you need to measure out some crushed limestone, sand, and iron, and cook it up in a big oven. The end result? Super powerful glue that's activated with water. The basic recipe for cement is simple enough. What's tough is making huge amounts real fast without making a mistake. One tiny error in the formula ruins the whole batch. So what makes limestone so special? Cement needs calcium. And limestone started out as the calcium-rich shells and skeletons of small prehistoric ocean dwellers. It's the calcium in cement that gives it properties necessary to help form concrete. And it's the cement plant's giant pestle and mortar that starts the rock crushing. Giant pieces of rock are dumped into it as the center cone sways back and forth to break it up. In seconds, this machine reduces a rock as big as your dining room table to chunks the size of a grapefruit. The trick to keeping this all going is a steady supply of rock. No way you could ever ship this stuff and stay in business. That would cost way too much. So for a cement plant, location is everything. This is the limestone quarry next door. When it runs dry, the whole shooting match has to pack up and move to a new location. To get at the limestone, it's hacked off layer by layer in an open pit. Explosives are packed into precision-drilled holes along the mine's leading edge. The charges are set off like dominoes, all of them detonating in less than a second. One blast frees up 50,000 tons, which will keep this crusher fed for up to 5 days. The chunks fall from the primary crusher onto a conveyor belt for further refinement. But the rock still has to go through 2 more crushers before it's reduced to a dust so fine that it could pass through your home coffee filter. Next step, the rocks are delivered to the hammer crusher. And it beats them into golf ball-sized chunks. Now, add iron and sand. The mix has to be perfect, so machines monitor it every second. They can adjust the mix on the fly or send warnings to a control room. Now, it's time for the final crusher. And it's a big one, more than 5 stories tall. The mixed rock is driven under 50-ton wheels that do the crushing. If the amount of rock gets too low, sensors tell the conveyors to pick up speed. A huge vacuum sucks up dust from the crusher and sends it to these hoppers. From there, the dust is screened for impurities and stored in one of the world's largest silos. Mix water with what's in here, and all you'll get is gray muck. This stuff is still just rock dust. To become cement, it has to be superheated, then mixed with more ingredients on its way to becoming the ultimate construction glue. Heat is the critical catalyst in setting off a chemical chain reaction that turns the raw mix into the real thing. The stuff that hardens when mixed with water. For that to happen, you need to get the carbon dioxide out of the stone. And the best way to do it is to get things real hot, all the way to 1600 degrees Celsius. That's hotter than the core of an erupting volcano. It starts in this preheating tower. Heat from gas burners rises up through interconnected cones. Each one is 7 meters in diameter and 15 meters tall. The limestone powder swirls down through the rising heat, moving from one cone to the next, heating up as it goes. 5 cones later, it hits 900 degrees Celsius. And that's the magic number. At this temperature, it creates new bonds and frees carbon dioxide stored in the limestone. Next, you need to bond the dust back together by melting it in this kiln. At one end, a giant flamethrower that slides between 2 blast-proof doors. Fuel blows down its length and explodes into flames 10 meters long. Hundreds of air compressors stoke the fire with blasts of oxygen. Advanced thermal imaging cameras keep constant watch. Temperatures have to be kept steady to make sure the product is consistent. And that's just one of the problems maintaining a blaze this powerful in a kiln this big. You also got to stop it from clogging, twisting out of shape, or developing dangerous hotspots that could shut the whole thing down. To prevent backups, the kiln never stops turning. That action keeps the mix tumbling, like clothes in your dryer. And since it's designed with a downward slope, each rotation carries the mix a bit further. The twisting force is strongest near the motor and loses torque further out. So these support tires have a flexible inner ring that allows the outer section of the kiln to slip, making up for any lag in rotation and keeping everything turning together. The rings relieve pressure that builds up from the high torque twisting. Without them, the kiln would tear itself apart. By the time the mix reaches the other end, it's a scorching 1500 degrees Celsius. Machine-made lava. So the kiln has to be lined with ceramic blocks. Hundreds of thousands of them. They're tapered, so when you stack them together, they form a circle, supporting each other like an arch. Even with the blocks, the outside of the kiln can get dangerously hot. So technicians use infrared cameras to locate trouble. Problem spots get immediately blasted with cool air from massive fans. Even then, the heat and friction take their toll, and eventually turn blocks from this into this. When that happens, the kiln is shut down. It takes a full week for it to cool enough for maintenance crews to do the repairs. The bricks last for about 12 months each, giving the kiln enough time to make about 2 million tons of this material. It's called clinker, and it's what you get from all that cooking. Basically, dust that's been partially melted back into rock. The clinker is cooled on vibrating grates in a building connected to the kiln. The material is then picked up by a conveyor and sent on its way to be mixed with the final ingredient, gypsum. It slows the chemical reaction that begins the moment you add water to cement. Both gypsum and clinker are put on precision-controlled conveyors. 95% clinker, 5% gypsum, and fed straight into a rollerball mill. Inside, steel balls pound everything into microscopic dust. By the time these machines are done, the powder is so fine that compressed air simply blows the finished product up these pipes and into storage silos, ready for pickup. Just 3 hours ago, this rock was part of the Earth's crust. Now, thanks to the machines in this cement plant, it's ready to build bridges, roads, buildings, and pretty much everything else you see around you. This is a Super C-Class ferry, a vital transportation cog working the coast of British Columbia, Canada. With way too much water for a bridge between the mainland and nearly 1 million residents who live on these islands, ferries are the only practical way to move thousands of people, their vehicles, and countless goods back and forth every day. This 160-meter, 10,000-ton ship can haul almost 2,000 passengers, 370 cars, and 32 tractor-trailers at the same time, making it and its two sister ships the largest double-ended ferries in the world. And that means more than having two doors. You need two wheelhouses, two propellers, two rudders, and 4 giant diesel engines. And then you need some advanced engineering and safety systems to keep it all floating. Let's see how it works. A double-ended ferry like the Coastal Celebration is basically a floating bridge powered by huge engines. You just drive in one end and out the other. This allows the ferry to load and unload all these cars and trucks in as little as 20 minutes. But this design creates a few problems. Having propellers on both ends is great for getting in and out of port quick, but how do you get them to work together? First up, propulsion. These monster engines crank up a pair of electric generators, powerful enough to supply a constant source of electricity to almost 20,000 homes. All of this energy flows to giant electric motors, one for each propeller. To change direction, just cut off power to one and send it to the other. The machine's propellers have a variable pitch mechanism that gives them total maneuverability. So when not in use, the blades turn and tuck into a streamlined position. That's basically how you make a ship with no front and no back. But the Super C ferries are so big and powerful, they need special engineering to make sure the parts can stand up to the pressure. Each motor spins the propellers with over 21,000 horsepower. That's the equivalent of 600 standard outboard motors, made all the more efficient by a flex cam system that adjusts each of the engine's pistons hundreds of times every minute. All that power puts a lot of strain on the shafts that connect the motors to the propellers. So special oil-filled rings support the shafts and prevent warping or twisting from all that torque. One of the ship's enormous propellers is spinning on the other side of this steel wall, and it's got problems of its own to deal with. One of the biggest is a destructive form of erosion unique to marine vessels. Props this big create lots of bubbles and incredible amounts of water pressure. That's great for thrust and propulsion, but the action is also strong enough to compress air bubbles so much that they superheat and explode. It's a phenomenon called cavitation, and it would chew through the blades if they weren't made from a specially designed alloy that ensures long-term durability. The Super C's designers put a lot of thought into safeguarding mechanical parts on these ships. But what about the passengers? Fire is always a huge concern for ships at sea. Select crew are trained as firefighters, and each ferry has its own team. But if fire breaks out on a ship, you have very little time to stop it before it gets out of control. So in keeping with all the other bells and whistles on this machine, they installed a unique fire protection technology that knocks out blazes before they can spread. Their system combines the suppressing strength of water with a knockout punch of anti-fire gases without risk to passengers or crew. The Super C-Class ferries use a high fog system that can put out just about anything in under 5 seconds. And it does it with 90% less water than a traditional sprinkler system. Nozzles are placed throughout the ship in key areas. Water is pressurized in this tank, then blasted through the nozzles that atomize it. The resulting mist blankets a large area while pressure forces the fog down to the heart of the blaze. The key to its success is reducing the temperature of the fire and knocking it out as quickly as possible. The system can be activated by temperature gauges, smoke alarms, or manually. There's plenty of other things to keep a crew occupied out here, like other boats. When you're this big, you sure don't want to hit them or knock them over with a big wake. So the hull is designed with wakeless technology. The wide top section floats on a narrow underwater section, perfect for cutting through the water. And even when cruising at 25 knots, it produces almost no wake. Up on the bridge, a state-of-the-art navigation system helps captains counter tides and currents, see through thick fogs, and make sure the ship arrives on time. They also have an autopilot system that's guided by GPS to help locate other ships. And when they're cutting through narrow channels between islands, there's a lot on the line. One wrong move in these busy waters, and the ferry could run aground. So one lucky crew member stands by, ready to drop the machine's giant emergency brake, the anchor. If the engine fails, it's dropped immediately, bringing everything to a quick stop. But what if things do go really wrong and the ship has to be evacuated? Where are all the lifeboats? They're safe, sound, and out of sight. These lifesavers are inflatable. In the unlikely event of an emergency, slides blast out the side of the ship and passengers take a 5-story ride. Massive self-inflating lifeboats wait at the end of the slide. Designed specifically for ferries, it's the fastest evacuation system ever made. And it leaves passengers free to enjoy their crossing and the view from high above the water, while saving a multi-billion-dollar expense of having to build a bridge over 40 kilometers of ocean. Besides, who wants to drive over a static bridge when you can slide onto a moving one that does the work for you? This is an Oshkosh Striker, a custom-built firefighting machine designed to protect airports and passengers around the world. If a plane crashes out here, the Striker's gotta respond in seconds, protect firefighters from jet fuel blazes, and put the fire out fast, even if there isn't a hydrant in sight. Toronto, Canada's Pearson International and its 5 runways are spread out over 18 square kilometers of uneven terrain. It handles over 30 million passengers and almost 500,000 flights every year. It's a great place to see the Striker in action and to get a sense of the challenges this machine has to overcome. Let's see how it works. To fight fires out here, you need superior firepower, extreme mobility, rock-solid stability, and total visibility. Fires fed by jet fuel pack a lot of punch, so you need more than regular lines and hoses to fight them. The Striker comes with joystick-controlled roof and bumper turrets that can attack flames from over 60 meters away. A design feature that is as efficient as it is powerful, thanks to the machine's high-powered water pump and its impeller. Water is sucked into the pump, then it hits the spinning impeller. Enormous water pressure is created by centrifugal force from the spinning action of the curved blades. Design features that allow a single firefighter to control a blaze. And if burning fuel ever threatens the Striker, it has 5 undercarriage nozzles to create a wet safety area on the ground around it. The turrets are fed by an onboard tank that carries 17,000 liters of water, enough to fill about 25 queen-sized waterbeds. And all that extra weight has to be moved fast. Jet fuel fires can rage at over 1,000 degrees Celsius, so they can burn through a fuselage in minutes. So every second counts. To reach crash sites fast, these machines need amazing speed and handling. Easier said than done when you're moving over 50 tons of aluminum and rubber. Speed starts with a 950 horsepower engine that lets the Striker hit 85 kilometers an hour in under 35 seconds. Onboard GPS plots the quickest path to the accident, automatically directing the Striker around busy airport roads and runways. That takes care of speed. Now you have to control it. Firefighters are always at risk racing to emergencies, so traction and stability are critical. A fully independent suspension lets individual wheels ride as high as they need to. All-wheel turning helps the operator with precision. The Striker can also deflate its tires to increase traction if it has to go off-road. And big clearances mean it won't get hung up on the way. A massive wraparound cab that comes with 80 square feet of glass and total panoramic views ensure drivers never get blindsided. Handlines also allow firefighters to get out and attack the blaze from different angles. With tools like these, the Striker can put out almost anything in record time. And it needs to. When a plane goes down, the passengers and crew have only a few moments to escape. Fortunately, with the Oshkosh Striker on the scene, they've got a fighting chance.